Hello, hello, and welcome to another London Gophers YouTube premiere. We have quite a unique talk this evening, and I believe it is our first TriCast. Before we get to the main event, let's quickly go over our JetBrains raffle. The code for this evening is Feather, and I think you'll know why in a moment. If you would like a chance to win a free JetBrains license, please head on over to that link and follow the instructions. Without further ado, time for the main event. Please welcome Raymond, Julien Lange, and Bernardo Toninho for Featherweight Go.
Hi, my name is Bernardo Toninho. I'm an academic from Nova University of Lisbon, and I, together with my colleagues Raymond and Julien Lange, will be telling you a bit about our work on understanding generics for Go. So this won't really be a tutorial on generics, but rather a look at generics for Go, or a design for generics for Go, from a language theory or a programming language theory perspective, and also from a bit of a more research point of view. So most of you likely have a pretty good understanding for what generics are already, but let's recap. So from a programming language perspective, generics give you a means to define data structures and functions or methods that manipulate data whose types are specified or instantiated really later on. So in some sense, they're the key source or a key source of modularity and code reuse in the programming language. Now, since Go doesn't have generics, how do we actually achieve modularity in this sense in Go? So you're probably familiar with the pattern, which is using the empty interface type, leveraging Go's structural typing system, as it's called, and then using type assertions or casts, which are runtime type checks, essentially, to then go back from the interface type to the concrete type instance that you're looking for. And this, of course, can fail at runtime. Or you can just forego modularity in some sense and just duplicate code by hand or by relying on some external code generation tool to do this for you. So are Go developers satisfied with the status quo? So one wonders, really, if this is a sort of good enough story. And as it turns out, well, developers have been quite vocal about the absence of generics in Go. Looking at data from the Go developer survey from 2019, 79 of respondents that said that Go was missing some critical features mentioned generics specifically, and 15% highlighted the lack of generics as sort of the biggest challenge using Go. And this has been consistent request over the years. So it's been the top 3 major challenges in adopting or using Go in developer surveys from 2018, 17, and 16. So given this, the Go team, so the group of people that maintain and develop the Go language, have been studying approaches to generics that are somehow aligned with the spirit of Go programming. One of the goals is to have no compile time programming like you have in C++ templates. So you want this design or the idea of generics to be simple enough. And moreover, it has to have a sort of a similar look and feel to that of Go of today. So typing should be structural, or duck typing as it's often called. Moreover, it has to be mostly backwards compatible. So one of the early proposals that was put out from the Go team was an idea called contract. So contracts specified the requirements or the operations of a set of types, really. And then the idea would be that functions would be declared with type parameters that would be bound by contracts. So the types would have to satisfy the contracts or the operations specified by the contracts. So let's look at what this looks like. So a simple example of this concept of contracts is a stringer contract, which we have here on the slide. So the idea is that you can specify the stringer contract, and notice that this is a new keyword in the language. And so the stringer contract really is just a specification that the type T here, that is supposed to satisfy this contract, must implement a string method, which produces a string. Contracts would then be used as bounds to type parameters and functions. So for instance, the stringify function that we have here takes a generic slice of type T, where T is then bound by the stringer contract. And so you can now produce the corresponding slice of strings by calling the string method in the natural way, ranging over the elements of the slice. Okay. So the contracts proposal also allows for contracts over multiple types, as it were. So for instance, the via strings contract holds for a pair of types that can be mapped to and from strings. So it's a bit of a more general idea than the stringer contract. And so what this allows is for multiple type parameters and functions, which then must be bound by a single contract in this way. So for this set via strings function would then take two type parameters that both in this via strings contract, and then you can use this more general version where you have a slice of type from and you produce a slice of type to by using both the string and the set methods specified by the contract. In terms of type definitions, the contract story is more or less what you'd expect. So type definitions can now take type parameters that are bound by contracts, and you can then have methods which are defined generically in the more or less expected way. Now, if you think about this for a while, which we did, it's not very clear what contracts actually are in some sense. How are they different from some version of generic interfaces? Do they do more than what one could do with interfaces? And so at this point, we academics got involved with the Go team following this challenge by Rob Pike to Phil Water, one of our colleagues, on trying to figure out what polymorphism should mean or look like in a language like Go. So our initial approach, given this contracts proposal, was to figure out essentially what contracts are, what they mean, using our sort of programming language researcher theory tools. Namely, we wanted to figure out if we actually needed to add this new thing, this new keyword to the language to achieve the intended goals. Even though you're only going to hear from me, Julien, and Ray today, this is actually quite a large team, including people from the Go team like Robert Griesmer and Ian Taylor, but also a bunch of other academics which are listed here. So in a broader sense, given the existing body of work in generics and polymorphism and in various programming languages, our goal was to really see that if we can draw upon the lessons learned from this body of work and from PL theory, programming language theory in general, and apply them to Go. Our main design constraints, as it were, would be to have no compile time programming, as I mentioned before, so to keep things simple, to have the same similar look and feel that is wanted from generics in Go, so familiar in some sense, and to have it be non-breaking, a non-breaking change, so backwards compatible. So what we did was develop a very small core formal model of Go called Featherweight Go, which captures the key features of Go, namely structs, interfaces, methods, type assertions, and crucially, the kind of duck typing or structural typing that exists in Go, namely that you don't have to declare that a type implements a certain interface. And from that, we generalize the model to featherweight generic Go, essentially by considering parameterization in struct, interface types, and in methods. And even though covariant receiver bounds is in bold in the slide, I'll show you what that means exactly in a few slides. And we also studied how to implement this idea of generics using a technique called monomorphisation. We chose this approach because it was really identified by the Go team as a key part of the desired implementation approach. And what this means in practice is that this is a mapping from featherweight generic Go to featherweight Go. So in some sense, it's an explanation of generics in Go using very small formal model of Go. And actually, from a theory perspective, this is one of the first formal works on monomorphization with a structural subtype. So what is featherweight Go? So it's actually, as I said, a tiny but Turing-complete functional programming language that aims to distill the core features of Go. And we designed it such that all valid featherweight Go programs are actually Go programs. So I'm now going to show you some simple featherweight Go code, which is actually just Go code. This is a definition of an EQ interface, so for types, with an equal method. And we can define an equal method for int by doing a type assertion, converting the parameter that, which must itself be an EQ, to type int, which we can then compare. Okay, so we can also define richer types in featherweight Go. So we can define a pair type, which is really just a struct containing two elements, using the empty interface to type the left and right components of the pair. We can have pairs implement the EQ interface using essentially a bunch of type assertions. We have to convert the element that we are testing for equality to the pair type using a type assertion. And then we have a similar situation where we have to convert the left and right elements of our pair to the EQ interface to then call the equal method on the left and right components of P, which is the converted argument. And well, we can define a pair of ints in the expected way. If all works out, it will be equal to itself. So as I mentioned earlier, in terms of generics, what we did was take our core subset of Go, essentially, which is Featherweight Go, and consider an extension of this language with generics drawing from standard programming language approaches. We also formally prove that these two languages, Featherweight Go and Featherweight Generic Go, are good in some sense. So what does that look like? Well, more or less like this. So I won't really go into the details, but the overall idea is that we formally model the type system, essentially what it means for a program in the language to be well typed. And we also have to give a model of the execution semantics of a program. And what we then do is show that the execution semantics and the typing system are somehow in harmony, which is usually called type safety. So you might have heard before the slogan that safety or type safety is progress plus preservation. So preservation or type preservation means that the type of a well-typed program cannot change during execution. Progress states that a well-typed program is either a value, a literal, say, or it can always take an execution step. So it always has a well-defined semantic. These two results make up type safety because the combination of the two results states that your program cannot reach a state where it does not have a well-defined semantic, so where it cannot execute further, and it's not a value. So we have shown that Featherweight Go is type safe. So let's move on to Featherweight Generic Go and see what it looks like. So we're going to just revisit this EQ interface using Featherweight Generic Go. The EQ interface becomes parameterized by a type that is itself an EQ, and the equal method takes an argument of that type. Now, how do we implement equal for int? Well, the whole point here is that we no longer need this cast. So in Featherweight Generic Go, we can actually statically enforce that the argument must be of type int. And in this setting, of course, we no longer need to have the cast or the type assertion. Similarly, the left and right elements of a pair no longer need to be of empty interface type. They can be of a generic type. Pair is now parameterized by two types because pair elements can have different type. And so left and right are now of type A and B. So they can be of any type. And what does equal look like for pairs? Well, now what happens is that this particular definition of the equal method here is defined on pairs whose elements A and B are bound by interface EQ and not any. So essentially what we're doing is we're specializing the method receiver to match what we need to then implement the equal method in the natural way. So this kind of specialization of method receivers is actually something that we can get for free from our theory. And okay, so how do we actually use parameterized types? Well, they have to be instantiated with the appropriate types. So pair now becomes a pair applied to int. So in a nutshell, Featherweight Generic Go, or FGG, extends Featherweight Go with type parameters in structs, methods, and interfaces. And type parameters can have interface bounds. Methods can be attached to generic structs, but as I've shown you, bounds can be specialized. But the way subtyping or the implements relation in Featherweight Generic Go works is actually the same as in Go. So it should feel the same as programming in Go. And as I showed you, virtually no casts are needed. So you can be more precise when you write your functions and methods. Formally, we did the same kind of exercise, if you will, as before. We defined the typing system and the semantics of FGG and show that it essentially retains type safety, progress, and preservation in the sense that I've mentioned before. So if we take stock of what we did and go back to our original question regarding contracts, it turns out essentially that we have shown that we can subsume the need for a contracts mechanism by just using generic interface. So we get a very clean account of generics by just grounding it in programming language theory. And we get a form of generic duck typing without contracts. And we can get a few more extra features for free, making the design robust. So I've already mentioned the specialized receivers, but actually we have support for extra type parameters in methods. So if you wanted to define a functional like map function, you could do it in our setting by defining an extra type parameter for this map method, which then allows you to go from a list of type A to a list of type B using a function from A to B. And we also have the ability to define mutually or self-referencing type parameters, which can be useful in some instances. For instance, if you're trying to model a graph, here is one way of doing it. So you can define a node interface, which is parameterized by the type edge. So a node has an edges method, which gives you a slice of edges. And edges can be defined as a parameterized interface, specifying a nodes method that gives you the nodes that the edge links. And then the graph struct is parameterized by two types, node, and edge, nodes being linked by edges, and edges linking nodes. So this is Featherweight Go and Featherweight Generic Go, and a little bit of insight into our design. So now Julien is going to tell you a little bit about how we can actually realize our design for generics in an actual implementation.
Right, so at this point, we have a good solid design language or language extension. But this language with generics is very high level, it's very abstract, which is good because it means that the developers have to write less code. But it also means that the compilation, so the compilation to machine code, will require more work. So a key design choice here is where and when should this work take place? And answering this question is a key objective of programming language research. Now, research in programming languages is all about trade-offs. It's about to find the right trade-off for the right language, for the right domain. And typically we choose between three sort of dimensions. We have the developer effort, so how much do we expect a developer to do to produce good code? So should the programmer think of memory allocation, for instance? The other dimension is what happens at compilation time. So how slow is the compiler? How much time does it take to produce some good code? How complicated the compiler might be? These sort of things. And the last dimension is at runtime. How slow will your program run? How complicated the runtime environment should be? These sort of things. And a typical example to really illustrate this sort of trade-off is the one of memory allocation. So if you think of how you deal with memory in a language like C, well, the programmer has to do that all by themselves. They have to allocate memory, free memory, these sort of things. On the other hand, a language like Go, using a garbage collector, will then free the developer of all these constraints. But it means that at runtime, a garbage collector must run and take a bit of resources to free the memory that is not used every now and then. So that is the memory allocation or management analogy, but what happens in the world of generics? Well, let's look at a few other programming languages. As you know, generics have been around for quite a few years now, and they've been around in quite a few different languages, implemented in many different ways. In Java, for instance, the language uses what we call static erasure and boxing. So it means that at compile time, a generic type, such as a list of bool, will actually just become a list. So the inner type argument here is actually erased. And this is done after type checking, of course. In the .NET framework, things are quite different there. Thanks to the JIT compiler, the just-in-time compiler, specialized code can be generated at runtime there. So this means that if the program needs a list of bool at runtime, a specialization of this list for booleans will be generated at runtime. The compiler doesn't do that much work, but actually the runtime environment needs to be quite clever, and there will be a cost at runtime because whenever you call list bool for the first time, you will need to generate code for that. And the last technique is monomorphisation, and this is what I will talk about more. Monomorphisation is used in Rust, Milton, and C++. Milton is a compiler for ML. The idea of monomorphisation is that all the code is generated at compile time. So if you need a list of bool, you will generate an instantiation and implementation of list for booleans at compile time. Everything needs to be done by the compiler there. So there is a cost. The compiler might be slower, but there is no runtime overhead. And even though it is a very simple approach in principle, and it's widely used, there is surprisingly little theoretical research about monomorphisation. Even though we'll be talking about monomorphisation a lot today, this is actually not the whole answer for Go. Monomorphisation will definitely be part of the implementation of generics, but because it's always quite a trade-off, the Go team is looking at combining monomorphisation techniques with other more scalable techniques for the final implementation. And just to be clear, the pros are there is a very low runtime overhead, so the programs will run as fast as non-generic code. It gives us a very concrete semantics for the generics, so we have a very concrete tool to communicate the design of the generic Go with the community. And it also gives us a first direct implementation strategy. But of course, it's important to bear in mind that monomorphisation is quite costly. It requires a whole program analysis. So you cannot monomorphize component by component, package by package. You might have to look at the whole program at once. It might generate a lot of code. There is a potential exponential blow up in the amount of code the compiler would produce. And finally, not all programs are monomorphizable. So in the context of this talk, you can think of monomorphization as a translation from Featherweight Generic Go to Featherweight Go. And the idea is that every parametric type or method or function in generic Go would be translated to a family of types, methods, functions in normal traditional Go. And there will be one instance, one implementation of such types, method, function for each instance that occurs at runtime. So now the challenge is, how do we know that this translation is good? Well, there is two properties we want to satisfy. One is that we want it to preserve typing. So it means that if we start with a program that is well typed, so that the generic compiler will accept, then the translation of that generic program is also accepted by the traditional Go compiler. And also, the behavior of the generic program should be the same as the behavior of its translation. The translation should really preserve what we intended. This also means that if the generic program is supposed to crash, then its translation is also supposed to crash as well, and vice versa. Now, I think the best way to explain to you how monomorphisation works is using an example. So let's do that. I'm going to start with our favorite FGG Featherweight Generic Go example. And that's the one with a simple list implemented in a very functional way that has only a map method defined on it. So what we have here is a list that can contain elements of type A. And the list is an interface that has only one function, and it's the function map, which is also parameterized by a type B. And map will essentially transform every element of the list of type A into something of type B. And it does that by applying a function f on every element. So this is an interface, so we need to implement this in some way. And we have two implementations of this list. We have the empty list and the list that is not empty, so that has one element. So the empty list is fairly straightforward. It's just a struct that is empty, and it has a map defined on it, which has the same signature as my interface there. And all it does is return the empty list, which is now of type B. So this is the list of type A, and it returns list of type B. And we need to annotate this type here to help the FGG compiler, but we hope that in the future these annotations are actually not required. Then the non-empty list is a cons, and a cons of type A, and it has a head, so the element of type A, and then the tail, so the rest of the list, which is then the interface list again. And cons implements map as well, and map simply returns cons of type B and applies f on the head of the list, and then recursively applies map on the tail of the list. And if you want to use that list, it's very simple. You can create a list of two elements there with using cons twice and nil at the end. And then if you define this list xs, you can call map on it. I'm not giving you the function details just to keep the example short, but you can imagine that this call of map at the bottom there just takes a function that returns true if the integer is positive, for instance, something like that. So this is generic code. Now we need to translate it to something that is lower level, so less abstract. And in this case, actually, we want to generate something that the traditional Go compiler will understand. And to do this, we proceed in two steps. The first step is to guess what are the types that will actually be required at runtime. And we need to do that statically. And once we have this list of types that we will need at runtime, then we can generate some code. Now the tricky step is really the first step, because we need to be conservative. So we need to make sure that all of the types that will be required at runtime will be indeed produced by the compiler. So we might generate more types than we actually need, but we know that any types we might ever need will indeed be part of the produced code. So the way we find out what types we need is by just going through the program and almost executing it. We first look at the main function. In this case, we can see easily here that we'll need a list of int, a list of bool, and we also have a nil of int and a cons of int. And I can infer that just looking at the last two lines of my code there. So these are types that I will need, but of course I also need to generate instances for methods or method signatures. And in the main function here, I see that there is actually a call on map. And this call on map is done on a list of int on XS, and it's a map to bool. So I need to record this too. The tricky thing is this refers to an interface, so a function signature, not a real function. But looking at the code at compile time, I'm not too sure which of these map functions will actually be called. So the safe way to proceed is just to generate any implementation of map here that is defined on some implementation of list of int. And because these two are implementations of list of int, I should also produce map to bool for both of them. So I will add these two in my list of types or functions that I will need to produce code for. Okay, so now I know that I will need these two functions. Of course, these functions have a body and implementation, so I need to look into that. So the way I do that is interprocedurally. So I will replace parameter A by int, parameter B by bool, and look at the body of this function. In this case, I will get nil of ball, and I'll do the same for cons. And all I get in this case is just cons of ball. So I will need to add these two there. And now I have all the types that could ever be needed at runtime. I've just omitted function here just to keep things simple, but actually we need to go to generate code for function A and B there as well. So at this point we have our generic code that the developer wrote, and we have a list of type instances. So we enter the second step of monomorphisation, which is code generation or instance generation. And we start by the main function. And for this, it's fairly straightforward. We simply replace parentheses by less than or greater than. So we focus on this bit of code and reproduce this sort of code where I really essentially just replace the parentheses by less or greater than. And you should think of these sort of names are plain Go type names. So here I'm assuming that the Go compiler will not complain if you give it less or greater than in an identifier name. This is just to keep things readable for this presentation. Okay, so the main function is done, and now we are going to go through the list here and generate code for each of these elements. First thing, we have list of int, and list of int has a function call, which is on map to ball. So what we do here is that we identify the generic code that matches that, which is this bit here, and we produce just code by saying, well, there will be a list of int, that's for sure. And this interface will need map to ball, so I also instantiate function here. And again, I'm ignoring the code that I would actually need to generate for this guy here. So I go from a very parameterized, very generic type to something very concrete here. Everything here is saying exactly what types it should use. And I am oversimplifying a bit here. I'm actually hiding something from you that Ray will talk about in a few minutes. Okay, so we have code for list of int. What's next? We have list of ball. In this case, there is no method call on this. So this will be simpler. We simply just produce actually the empty interface, again, in the naive way here, and Ray will talk about this a bit later. Next, I move on to structs, and first I start with nil of int, so the empty list of integers. And in this case, I find the generic code first, and I just replace things or instantiate things. So I will get nil of int, and again, I just replace A by int and B by ball. So now we have an implementation of the empty list for integers. Next we want cons, so the non-empty list. Again, we find the generic codes and we replace it accordingly. And here you see that I'm also instantiating the struct fields. And finally in my list there is these two types here on nil of ball and cons of ball, so the implementation of list on booleans. And these don't have any methods, so I just look at the type description for both of them and produce the required code. So at this point, if I put all the code that we generated all together in one piece of code, I get all of this. And remember that the steps are, you just conservatively identify all the types you will need at runtime, but you do that at compile time. And then you produce lots of code for each of these types. I mentioned that not all programs are monomorphisable. And one of the smallest examples we can think of to illustrate this is this example here. So here I have a very simple struct, which is parameterized by type A, and it just holds a value of type A. Box has a method called nest, and nest is recursive, so it might loop a few times, n times in fact. And the key here is that box is calling itself again with a new parametric type, where box is nested one more time here. So this is a case of polymorphic recursion. A polymorphic recursive method is a method that calls itself, and at every call, the type signature of that method changes. So for instance here, the initial call is on box of A, and the second call is on box of A. Now because at compile time I don't know the value of n necessarily, I actually don't know how many times box will be nested. So if I want to take a conservative approach and conservatively estimate all of the types I would need at runtime, I would have to produce infinitely many instances of box of A. So of course that would mean that the first step of my algorithm would not terminate. I would get an infinite set of instances, so that's not good. Now, it's quite difficult to identify what programs actually produce this behavior. It's clear that polymorphic recursion sometimes does produce this behavior, but actually it's not always the case. And in fact, you cannot come up with a perfect algorithm that would decide if and only if a program is monomorphisable. The problem is in fact undecidable. There is no algorithm. What we can do though is again come up with a conservative algorithm. So an algorithm that will tell us that surely this program is monomorphisable. The downside, of course, is that it might rule out programs that are actually okay. And the way we do this in our Featherweight Go paper is with even more Greek letters, which I'll spare you here. But essentially we define a predicate, so a predicate is a function that takes a program in this case and returns a Boolean. And the predicate is called no-mono. And essentially, if no-mono does not hold on your program, then your program can be monomorphisable. And looking back at our previous examples, for the list example, no-mono does not hold, so we can indeed monomorphize this one. Instead, for box, no-mono holds, so we cannot guarantee that we can monomorphize this example.
Here's a quick recap. We have a small core fragment of Go called Featherweight Go, FG, and we've extended that with generics. And this is well designed in the sense of some nice properties. FGG has type preservation and progress. And we've seen that some generic programs are monomorphizable, which means we can implement generic Go by statically instantiating the generic types as FG types, as regular Go types. In the last part of this talk, we'll look at two more examples of points to consider related to the design of monomorphization and the non-mono check. The first example, again a minimal one to illustrate the point that programs can dynamically create unbounded structures but still have statically finite monomorphizations. We saw in a previous example that intuitively recursion can sometimes cause problems for monomorphization. But in general, dynamic recursion is a separate issue from the static recursion between types that causes the actual problem. Let's take again our list interface, our generic list interface, and its implementations nil and cons, structs. A reminder that any is just the empty interface. We're going to write a program that builds increasingly nested lists. So we take some list and we can put it as the head of some cons. We can take that list and put it as the head of some other cons and so on. We can write that using just a small helper struct, just called D. It has two type parameters. A parameter that is some list of B, where B is any. So it takes a list of anything. And we can write a method on that struct called OK. This is a recursive method. It's going to call itself. And at each step, it takes some list of anything, and it will create a cons with that list in the head, and then call itself. And we can bootstrap that from the main with just a nil. Alternatively, in FGG, we could have written this example using generic methods. We could have moved the type parameters from the helper struct to the method itself, but we've written it this way to be closer to the current Go, the actual Go proposal, which doesn't have generic methods. And so this example, although it's recurses indefinitely and builds these larger and larger lists, it's statically monomorphizable. And the reason for that is, as we've been saying in English, we're just working up to lists of anything. We're building these cons, but the type that we declare is just the any type. And so the recursion from a type point of view is quite flat. We're just working up to list of any at every step. We're not actually trying to do anything with these lists, so we don't need to be more precise with the type information. So this program is monomorphizable. We statically find that we need a list of specifically any, and a nil of any and a cons of any, and that's it for these guys. And then for the helper struct, we find in particular that we need a D of specifically list of any. And so we have just one instantiation of our helper struct and just one instantiation of its method. Our formal definitions and proof of concept implementation, it uses these angle bracket-like Unicode characters to generate the instantiated types as regular FG, as regular Go types. So all of this code is just standard Go and can be compiled and run in the usual ways. This code is just copy and pasted from the output of our prototype implementation. It's open source, you can access it here. It's written in Go, but it's a very basic implementation. It provides static FGG type checking, interpreters for executing FGG programs step by step. It provides a static no-mono checking and an FGG to FG monomorphizer. It's published as part of our paper with our co-authors on this work. You can also try the official playground from the Go team. Here I'm just pasting in the same generic program that we've just seen. Just slight syntax change. The Go team changed from parentheses to square brackets after the paper was published. And here you can see the program's accepted and it runs, but it times out as you expect. To complete this example, we can go one step further and make it non-monomorphisable. To do that, we're going to change the method body, but actually it's going to operationally do exactly the same thing. It's still going to build this increasingly nested list. We're only going to change the types that are involved. Previously, we flattened the types in this recursion by saying that any one point we've just got a list of any, regardless of how nested the list was, it was just a list of any. Now we'll try to be a bit more precise and we'll say that, well, we start with a list B, but we're going to produce a list of a list B. Of course, this is no longer statically monomorphisable. If we try to put the new version of the program through the tool, it will detect that there is a potential recursive path. In general, this is a conservative check with a type nesting such that we potentially may not be able to statically enumerate all the types that we might need anymore. So this program is not monomorphisable. We can try to put it through the playground again. The official playground doesn't support this kind of explicit no-mono checking. If we try to put that through, we'll see that it basically blows up, trying to instantiate this ever-increasingly nested type. Fortunately, just blowing up doesn't distinguish programs that are conceptually not monomorphisable from cases where, for some reason, the types are just too large. One of the motivations for no-mono checking is for better development tooling and compiler feedback. The last part of this talk. We have FGG, and it's correct with respect to some nice properties. We have monomorphisation and no-mono checking. The last piece that we want is that monomorphisation is correct with respect to some nice properties. Say we have a safe and monomorphisable generic program. Then we can monomorphize it, and what we want, and what we do have, is that the resulting FG program, the resulting Go program, is itself safe. Now that's certainly necessary for a correct monomorphisation, but is it sufficient? Well, let's say that we replace monomorphisation with a silly tool that just turns all your generic programs into Hello World in Go. Now, Hello World is safe, so we could cheat you and say that we have a safe monomorphisation, but that's obviously not what we would consider a correct monomorphisation. Beyond safety, what we need is a stronger behavioral property to justify the correctness of our design. If our generic program can make some step, according to some notion of computation step, then what we want is that the monomorphized version can make a corresponding step. To be clear, that's not any arbitrary step, but there should be some correspondence between these. And in fact, our monomorphization is designed such that we can apply it to some intermediate program, if you like, this partially executed program. And doing so will give us exactly the thing that we're expecting. So this means that if we have a generic program and we execute it one step and then monomorphize it, that gives us exactly the same thing as monomorphizing it first and then executing it the corresponding step. And we have that all the way up until if and when the programs stop executing together. This kind of property is called a simulation property. We can say that the generic program and its monomorphization simulate each other. You can use the prototype implementation to play with this. You can dynamically test the simulation between the generic program and its monomorphization. We're not going to go into those technical details, but we will give one final example just to illustrate how this property can come into play, and it also touches on the interplay between monomorphization and Go structural typing. Okay, one last time. We'll take our generic list interface. We also have our nil struct. For this example, we don't need the construct, but we do need the map method of the list interface. The detail is not important, just that this is a generic method. It declares its own type parameter. We'll also use this very small helper struct called toAny. It declares a single field of type any. We'll use this just to wrap structs of other types and effectively upcast to any. And our program only does this. It creates a nil, it wraps it using our toAny helper struct, it selects that field, and then it uses a type assertion to assert that it's a list. So in other words, we create a nil, we effectively upcast it to any, and then try to downcast it back to list. And this program, of course, is fine, because a nil is a list. We want to monomorphize this program. Monomorphization is all about statically collecting up all potential instances of generic types and methods that we might need. The question is, how about generic methods that are never used? We simply never call this map method in our program. What should we output for a generic method if we don't have any instantiations for it? Can we simply omit this method like we do for type combinations that aren't used? We can try to run with this as a naive monomorphization. If we say that this is the monomorphization, well, in fact, this is itself a safe Go program, and we can compile and run it, and it will also satisfy the behavioral correspondence, the simulation property that we stipulated. As you can probably see, though, this isn't going to fly. Our program works, our type assertion works, basically because we've reduced the list interface to the same as the empty interface. Anything would pass this type assertion. So this naive monomorphization would be very easy to break. Say we comment out the map method for nil. This means nil is no longer an implementation of the list interface. Well, our original program is going to panic because the type assertion doesn't hold. But our naive monomorphization, that doesn't change at all. So at this level, it's going to run okay. And this now violates the behavioral property, the simulation property that we want to justify the correctness of our design. So this means that this design is not correct. This issue is due to the interplay between monomorphization and Go's structural typing for interfaces. To solve this problem, our monomorphization introduces what we call dummy methods. So in this example, even though we have no instances for this generic map method, we introduce a dummy method to keep this list_any instantiation separate from the list, separate from the empty interface, so that now in our correct monomorphization, the type assertion will correctly panic, just as we require. For completeness, we can restore the map method to nil, and so our original program works again. Of course, our monomorphization then has to generate an implementation of the dummy method for nil as well to make it a list. And so our monomorphized program will work correctly. This is obviously quite a simple example, but in general the point of monomorphization is that a correct design has to preserve all of the subtyping relationship in the original program in the monomorphized program. And care has to be taken, for example, to produce these dummy methods in a suitably unique way. For example, so that the monomorphized types don't have extra relationships to other types that they didn't have in the original program. That's all for our talk. Thank you for listening. Obviously, there are many important points to consider in a big job like adding generics to Go, which we haven't focused on. For example, syntax. We mentioned the Go team have redesigned the syntax at some point after we first published this work. Instead, we took a brief look at generics for Go from more of a programming languages and research view. We talked about how we can approach this work formally, with a focus on key language design properties, and in particular how we can justify the correctness of our design based on monomorphisation. This work is a collaboration between researchers and the Go team, and we published the paper at OOPSLA 20. But that's not the end of the story. You may have seen the latest language change proposal from the Go team, now based on interfaces instead of contracts. But the full details of the exact implementation approach are still being worked on. Monomorphisation looks like it will be part of the story, but not the whole solution. We're very happy to talk about any aspect of generics in Go, any questions or thoughts. We also work on tools for programming and verifying concurrent and distributed programs in Go. Feel free to get in touch and talk with us about any of these topics. We're always very happy to hear which points developers are most interested in.
What a fantastic talk. The way you guys worked together on this was truly amazing. Pulling the video together, the transitions, the information, the presentation. Honestly, that was truly excellent. I hope everyone at home enjoyed that as much as I did when I first watched it. Please give a virtual round of applause for Raymond, Julien Lange, and Bernardo Toninho. Please remember, the JetBrains raffle code for this evening is Feather. Enter for a chance to win a free JetBrains license. You have until tomorrow to submit your code. Well, looks like we're at the end of another London Gophers premiere. Thanks once again to our speakers, and thank you to everyone watching in the audience. And until the next time, please take care.